Hello and welcome everyone to this podcast for cell biology. In this podcast, we're going to talk about water and its role in life. We're going to begin by talking about water's importance. Why do we know it's important? Then we're going to talk about the structure of water and review hydrogen bonds from the last podcast. In this discussion, we'll talk about why water is important in dissolving polar molecules, but not nonpolar ones. We'll next talk about water properties. What unique properties of water allow it to play such an important role in life? Then we're going to talk about aqueous solutions. And then we're going to close with talking about functional groups. Functional groups isn't directly linked to water, but it's an important concept that we need to cover before we move on. So let's begin by talking about the importance of water. And to begin this discussion, let's remind ourselves that water was essential for the evolution of life. For that very first cell to form, water was needed. In addition, water is essential for life to continue. And so what are some facts about water and life that lead us to believe it's essential for life? Let's list a few here. We know that all organisms require water. We also know that greater than 75% of a cell is water, which means most living organisms are water, meaning you and I, we're greater than 75% water. Most, not all, but most cells are surrounded by water. The next one is that biological reactions require water. And the last thing I want to say is that we can live for several weeks without food. However, we can only live several days without water. As we begin to understand the importance and how water functions in cells and for life, let's take a step back and draw the structure of a water molecule. Now, before we draw that water molecule, I want to introduce a couple terms to you. Polar and nonpolar. Polar molecules contain partial negative charges and partial positive charges on opposite sides of the molecule. Some examples of polar molecules include water, sodium chloride, and glucose, or a sugar molecule. And I'm just going to draw the sugar molecule as a ring. And they can come in various sizes and structures. We're just going to draw it like this for now. So what makes these partially charged? So the water molecule, remember, contains a partial positive charge at the hydrogens and a partial negative charge at the oxygen. Sodium chloride, the sodium is positively charged and the chloride is negatively charged. Here we see the glucose molecule. The oxygen here is going to be partially negative and the hydrogens partially positive. They contain these partially positive and negative charges because of the atomic structure of the element, the arrangement of those electrons. What about nonpolar interactions? Nonpolar interactions form when electrons are equally shared. We don't see the partial positive and negative charges that we see with the polar interactions. So no partial charges. So some examples of nonpolar molecules include octane, which is what we use as gasoline, as well as lipids, fats. These are nonpolar. So let me say a couple other things about polar and nonpolar molecules. Polar molecules will interact with water. Molecules that interact with water, we say they are hydrophilic. So for instance, we could draw a water molecule here, like so, and since it's polar, partially positive here, partially negative here, it can interact with itself, or with other water molecules, I should say, because of the partially negative and partially positive charges on these oxygens and hydrogens, respectively. As another example, if we take our sodium chloride, and we'll put sodium here and chloride over here, the reason that sodium chloride or salt dissolves in water is because water molecules will surround it like so and form these interactions between them. So remember, again, oxygen has this partially negative charge, so it's going to bind with the sodium, and it will bind to it from multiple angles. Chloride also interacts with water, but it will interact with water with the hydrogens because of the partial positive charges on the hydrogen. The ability to interact with these polar molecules is why water is a great solvent. Nonpolar molecules usually do not interact with water. These nonpolar molecules that do not interact with water, we say they are hydrophobic. Phobic means to fear, hydro means water, so you can remember this by these molecules do not like water molecules. You can think of it as them fearing water molecules, so they don't interact with them. I should have mentioned that up here. Philic means to like or to love. So in this example, in hydrophilic examples, the water molecules like to interact with water. So let's think of an example over here. If we had a beaker and we added into this beaker fats like an oil, and we added into this beaker water, what would happen? Would we see this nice mixture of the two because the oil is dissolving in the water? Or would we see them separating from each other, where the water would be on the bottom and the oil would be on the top? And if you've ever looked at some salad dressings, you'll know that this is what we see. And the reason for that is because the oil molecules are interacting with themselves and are not, because they're not polar, so they're not interacting with the water molecules. The water molecules, still being polar, they're interacting with themselves, and they form this bottom layer. So oils and other nonpolar molecules are hydrophobic because they do not interact with water. And this is why nonpolar molecules, like oils and other fats, are poor biological solvents. Polar molecules do not readily dissolve in oil or other nonpolar molecules. Now, I've used some terms in the past several minutes that I haven't properly defined, so I want to take some time now and talk about solutions. So solutions is a liquid that contains one or more dissolved solids or gases. So what are the parts of a solution? There are two parts. There's the solute, and then there's the solvent. The solvent is the liquid that dissolves the solid or gas, whereas the solute is the solid or gas being dissolved. In cell biology, when we talk about solutions, we're almost always going to talk about aqueous solutions. Aqueous solutions are solutions where the solvent is water. So this semester, when we talk about solutions, you can assume it's an aqueous solution unless I tell you otherwise. And I can't imagine telling you otherwise because it's very rare that we'll talk about non-aqueous solutions. All right, now I'd like to talk to you about properties of water. More specifically, properties that give it that unique quality that makes it so important for life. The properties I want to talk about include adhesion and cohesion, and how that gives rise to surface tension. I'm going to talk about specific heat of water. Then I want to talk a little bit about heat vaporization. Then I want to talk a little bit about the density of water as a solid or as a liquid. And in that I'm going to talk about how water expands upon freezing. So let's begin with adhesion and cohesion. In describing adhesion and cohesion, I'm going to draw a glass that's filled with water. And when you fill a glass with water, it will always form this meniscus. So this meniscus is seen here as water is being pulled up along the sides of the glass, and all the other molecules of water are in here. So let's first define adhesion and cohesion. So cohesion is the attraction between like molecules. So we say that water is cohesive because water binds to water. They're attracted to each other. They form these hydrogen bonds that we've talked about. Now, adhesion is the attraction between unlike molecules. In the case over here, this attraction is between the water molecule and the molecules on the glass. All these water molecules in here, they're binding to each other through cohesive actions. And as all these water molecules are binding to each other, it sort of pulls those molecules in a downward movement. Over here, the meniscus forms because the water molecule, the positive charges on the water molecules, interacts with the negative charges on the glass and pulls those water molecules up to kind of form this concave structure here, where it pulls it up. These two resist each other, pulling down and then pulling up on the sides, so that we see this ultimate meniscus. Now this is, I suspect, interesting if you're looking at a glass of water, but this is a cell biology class. This is a class about life. So why is this important for life? Okay, let's talk about something a little bit more biologically relevant. And so let's look at the surface of this pond. In general, this pond will have a fairly smooth surface. And that's because water likes to minimize surface area. That's why in a calm pond, we don't see something like this with the water. Now, if it's bad weather, you might get some disturbances. But a nice calm pond isn't going to look like this. It's going to look like this because it wants to have as small as possible surface area. This resistance to changing the surface area we call surface tension. I'm going to explain what I mean by that here. Remember, below this surface here, we have lots of water molecules. Too many to count. Lots and lots and lots of water molecules. And let's also remember there are many water molecules right at the surface too. All these water molecules are going to form hydrogen bonds with each other through the process of cohesion. They're also going to form hydrogen bonds with these water molecules at the surface, and at the surface they're going to interact with their neighbors through hydrogen bonds. Individually, remember, hydrogen bonds are very weak, but together they form this very strong structure here. And this is why it's able to maintain this very small surface area and create this surface tension. And what I mean by the surface tension is anything that tries to break the surface tension and maximize the surface area will be met with resistance. The water is going to constantly try to fight against that. And if it's ever broken, it's going to reform. For instance, if I took a big rock and dropped it into a pond, the surface tension will be broken. But as soon as that rock falls to the bottom, that surface tension will immediately be reformed. However, there are some things that are much lighter, say, than a rock, that won't break this surface tension. For instance, we may have a bug. I won't try to draw a bug. I'm just going to draw the word bug. Okay, and it's going to have its legs here that will be able to walk along this surface because it's not strong enough or heavy enough to break this surface tension. Because these water molecules are binding to each other through cohesion, and the molecules from the bug's legs and the water molecules below are interacting through adhesion. Okay, next I'd like to talk about the importance of water density. Liquid water is more dense than solid water. So let's write the opposite here. Solid water, or ice, is less dense than the liquid water. Another way to think of that is that you can get more water molecules into the same amount of space than you can get solid water molecules. So why does this matter? Well, it matters for lots of reasons, but as an example here, let's think about a pond. In the summer, it's all liquid. And underneath the water, or in the water, we have all kinds of life. In the winter, this life needs to continue to exist. And so when the temperatures drop below freezing, it's important that the whole pond or lake or other body of water that we're talking about here doesn't freeze. If it all froze, then this life would cease to exist. But since solid water, or ice, is less dense, as the cold air hits the surface here, it will begin to freeze the surface. So just let's draw this here. And this is my ice that begins to form at the surface. If ice was more dense than water, it would sink. And then the next layer of water would freeze, and it would sink, and so on and so on and so on, until the whole lake was frozen. Fortunately, this doesn't happen, because solid water is less dense. It's going to float. And now it serves as an insulator. Though at the very surface here, it's ice cold, below here, life can exist, and the water temperature doesn't change nearly as drastically. So how does this happen? So in ice, each water molecule will form 4 separate hydrogen bonds with adjacent water molecules. It's a very fixed structure. It's very rigid. In liquid water, water molecules will constantly form and break hydrogen bonds with other water molecules. At any given time, each water molecule may be bound to 1 other water molecule, 2, 3, or 4 other water molecules, but they're constantly forming and breaking. And because of that, these water molecules pack tighter with each other. They're less rigid. So up here in ice, the water molecules are very rigid. There's a lot more flexibility here in the liquid water, which allows them to pack tighter to each other and increases the density. But the main take-home point is that ice is less dense than liquid water, which allows it to float, which allows life to continue to flourish under the water in times of freezing conditions. Next, I want to talk about the ability of water to absorb energy. Water has an amazing ability to absorb large amounts of energy. And in talking about this, I want to talk about a couple terms. The first is specific heat. Your book gives a very good definition of specific heat, but for our purposes, what I want you to think of as specific heat is the amount of energy required to change the temperature of a substance. Water has a high, very high, specific heat, meaning it takes a lot of energy, a great amount of energy, to change the temperature of water. So remember, in our now famous pond here, and we talked about all those water molecules below the surface and at the surface, and the very strong network of hydrogen bonds that were forming between all of these made this surface tension very strong. So when a source of energy hits this, say from the sun, before it's going to change the reactivity of the water and change the temperature, it's got to break these hydrogen bonds. But if enough heat does come from the sun, or the energy from the sun in the form of heat, enough of it can penetrate the surface here, and the water molecules, these hydrogen bonds, can be broken and the temperature will go up. But it does take a great deal of energy. This is also why when you heat a pot of water on the stove, it doesn't immediately start to boil. It requires a lot of energy in the form of heat to change the temperature of water. This is also critical in maintaining a certain level of temperature so that life can continue to exist within this pot, but also within any given cell. Similar to the specific heat, let's also briefly say something about the heat of vaporization. And this is the amount of energy needed to convert liquid water to a gas. Another way you can think about this is that water requires a great deal of energy to form a gas. So let's draw the surface of someone's skin here. As one sweats, I'm just going to draw small droplets of water here. In order for this to vaporize and form a gas, these water molecules have to absorb a great deal of heat from our body in order to cause them to form a gas. So I'm going to say this again. On a hot day, sweat will form on our skin. In order for it to vaporize and form a gas, your body has to release a lot of heat into these water molecules, our sweat, in order for them to vaporize and form a gas. This allows our body to remain cool on very hot days. Okay, I think this is a good stopping point for the first podcast. And so in this podcast, I want to summarize real quick what we went over. We spent quite a bit of time talking about the importance of water. We talked about how it was important in cellular reactions. We talked about the fact that it makes up the majority of our cells and that life could not exist without it. We then talked about water's structure. We talked about how polar molecules could easily dissolve into water because of hydrogen bonding with the water molecule. And we said nonpolar molecules did not dissolve in water. We also compared and contrasted hydrophobic and how that hydrophobic molecules were usually nonpolar and did not interact with water molecules but interacted with themselves. And that hydrophilic molecules were typically polar molecules and did interact with water molecules in order to go into solution to dissolve in water. We talked about several properties of water. We talked about adhesion and cohesion, and we talked about specific heat and the heat of vaporization, and we talked about how the solid form of water is more dense than the liquid form of water. In the next podcast, we're going to spend time talking about acids and bases and solutions, and also functional groups. If you have any questions about this material, please make sure you come see me. If not, I'll see you in class. Bye.